Hello, welcome again. Now today we'll start next topic, electric potential at any point due to an electric dipole. Now due to electric dipole we have to find out electric potential at any point. So we have to consider first electric dipole having two charges equal and opposite charges minus q and plus q and whose center is O and dipole length is 2L. So now we'll consider a point P. This is the arbitrary point P where we have to find out electric potential, and its distance from the center of this electric dipole is R. So now let the distance of P point from this minus q charge is R1. Let this point be A, and from plus q charge let it be R2, and let us suppose this point is B. Now electric potential at P due to minus q charge is V1, that is equal to 1 upon 4 pi epsilon naught q upon R1, because we know that the electric potential due to a point charge is equal to 1 upon 4 pi epsilon q upon R1, but charge is negative, then potential will also be negative. Equation number 1. Similarly, due to plus q charge, it is V2, that is plus 1 upon 4 pi epsilon naught, because charge is positive, R2. Equation number 2. So total potential is V is equal to V1 plus V2, which is equal to 1 upon 4 pi epsilon, and Q, that is constant, and will write 1 upon R2 minus 1 upon R1. This is equation number 3. Now we have to find out R2 and R1, because Q constant value 4 pi 1 upon 4 pi epsilon, that is also constant value. So when we'll calculate R2 and R1 and put in this equation number 3, then we are able to find out the electric potential V at point P. For that we will do one mathematical treatment, or we can say that a mathematical strategy will apply here to find out R2 and R1. So for that, what we'll do, we will produce this OP backwards. Here space is less, I forget to leave the space, but we will produce OP. This OP we will produce backward, and we will draw perpendicular. This perpendicular. I am writing here C. Similarly, we will draw a perpendicular on OP. At this point I will take D, this perpendicular. So draw AC perpendicular over OP. Also BD perpendicular over OP. Now you see R1, this R1, that become equal to AP, and which is approximately similar to PC. R1 which is equal to AP, which is similar to PC, approximately similar to PC. You see if this angle is very very small, this angle is very very small, this angle is very very small, then this AP become equal to PC. This is mathematically. So we can write PC is equal to OP plus OC. Now we know that OP is equal to R plus this is OC. So if this angle, let us suppose this OP make angle theta. So this opposite angle also is equal to theta. And in this triangle, when we will apply cos theta, then this distance OC, that is from triangle AOC, OC become is equal to L cos theta. Then here we write L cos theta. This OC become is equal to L cos theta. So similarly we can write R2 which is equal to BP, which is approximately equal to PD, and which is equal to OP minus OD, and OP is equal to R, and from triangle BOD, OD become is equal to L cos theta. Here we write L cos theta. This is also equal to, this OD also is equal to L cos theta. So this is R1, this is R2. Now we will use R1 and R2 in equation number 3. By using this mathematical treatment, we have calculated R1 and R2. Now R1 and R2 we will put in equation number 3. So we will get V is equal to Q upon 4 pi epsilon, which is equal to 1 upon R2, that is equal to R minus L cos theta, minus 1 upon R1, that is R plus L cos theta. Now further we will solve it, we will simplify this equation. So here this is the LCM of these two denominators. So we will solve it further. We will write here V is equal to Q upon 4 pi epsilon naught. The LCM that become is equal to R square minus L square cos square theta, and which is equal to R plus L cos theta minus R plus L cos theta. Mathematically we will simplify it. So this get cancel, we left with Q 4 pi epsilon naught, and this is 2L cos theta, R square minus L square cos square theta. Now because Q into 2L is equal to P, so we will write P is equal to P cos theta. This term Q 2L become, that is P over 4 pi epsilon naught R square minus L square cos square theta. So this is the electric potential at point P. So by simply knowing the value of theta, we can calculate electric dipole moment. And you remember that is theta is angle between electric dipole moment, direction of electric dipole moment, and OP. You can see the diagram clearly. This theta is the angle between P and OP. That is the distance of observation point from the center of the dipole. So here if we consider one case, if P this is electric dipole moment P lies at very large distance, or R is greater than L, or we can say that for small electric dipole we can neglect L. So V is equal to P cos theta 4 pi epsilon, and this L is neglected, we get R square. This is the electric potential at point P due to small electric dipole. This is a special case, we can say. So further we can write, because P cos theta is equal to P vector and R unit vector, where the value of R unit vector is equal to P, and this cos theta will be removed by this dot, and we will write it P vector, R unit vector, and 4 pi epsilon naught and R square. So now this dot product of two vector quantity is a scalar quantity, and we already know that potential is a scalar quantity. Next we can write special case if theta is equal to 0 degree, that is electric dipole moment is parallel to OP vector, or P lies on the axial line of dipole, then V becomes equal to P R 4 pi epsilon naught R square. This is unit vector, so that further become V is equal to P 4 pi epsilon naught R square, or V inversely proportional to R square. And second case is if theta is equal to 90 degree, that is electric dipole moment is perpendicular to OP, or P point lies on the equatorial line, then V is equal to P 4 pi epsilon naught cos 90 degree upon R square is equal to 0. So we can say that electric potential on the equatorial line that become always 0, and if we study about the variation of electric dipole, the variation of electric potential and distance from center of dipole, then we will get this type of the graph, or variation, we can say variation. So here we have a dipole, here plus q, here minus q, and this is the center. Okay, so if we consider point P on the axial line, we can say that at distance R, here we'll get a potential V. If we take further R, it become from the center total distance become 2R, then potential will get reduced 4 times. If we take one more R, the total distance become 3R, the potential that reduce 9 times, and in the same way. And on the equatorial line, this is second R, this is third R. From the center of the dipole, electric potential at every point that remains 0. So this in this way we can study the variation of electric potential with respect to R. This is our axial line, this is our equatorial line. So you need to do the derivation thoroughly once or two or three times, then you are able to understand. And thank you.